Finding the displacement from velocity time graphs. Once again, we have a velocity time graph, or a VT graph, of a bicycle that travels at 6 meters per second. You read that right there. And we'd like to know how far it travels after 5 seconds. Well, we know when we took the slope of the line, we found the acceleration, which was 0. What else can we do with that line? We can actually find the bicycle's displacement, which is its final position minus initial, with the formula for constant velocity. And you might say, well, how is that going to work? Well, here's our formula. V is equal to delta x over t. Let's multiply both sides by t. Okay, we undo the division by t, move the equation left to right. We have delta x is equal to vt. So what does that mean? Here's our velocity. It's constant. Okay, so that fills in for the v part. And look at our time. This is a change in time. That's going to be, well, t here. We just change in time we typically just write as t because we normally start time at 0. What are we doing there? We're actually finding the area of the rectangle under the line. So looks like I made the this parentheses a little too far. We want to stop at 5 seconds. That's actually a common error, so I'm glad I showed that to you by accident. We want to find this area of the rectangle. Okay, so that's going to be v times t. What are the units going to be? Well, it's meters per second times second. So meters, that's its displacement. So we're finding the area under the curve to find the displacement. Looks like I got a little ahead of these slides here, but let's go over them now as a nice review. We have a bicycle traveling at 6 meters per second for 5 seconds. We use the equation for the average velocity rearranged to solve for displacement. We put the numbers in, 6 meters per second times 5 seconds, and we get 30 meters. We can also find that displacement without using this equation. We're not going to use it. How? And well, I already said it on the last slide, but look at the area here, right? Where the boundary for time is 5 seconds, which is what we have here. And our velocity is the same at the whole point at 6 meters per second. So what are we going to do? We take the area of the graph that is bounded by the velocity and the elapsed time, which is 5 seconds. The area under that graph is the area of a rectangle, which is height times base, or base times height. And that area will be vt, and that will be the displacement. Now notice I've been calling this thing a curve, and you'll say, wait, that's a straight line. It sure is, but in physics, any line on a graph, whether it's a straight line or a curve, we go ahead and just call it a curve. We just had a graph where the velocity was constant, and we found the displacement by taking the area of the rectangle under the boundaries of the velocity and time. But what if we have a case like this, where the acceleration is not 0? We have the speed going from 0 meters per second, up to, looks like 8 meters per second, somewhere around 7 seconds. So, how do we find the displacement now? We can still find the area under the graph, except this time we have a different shape. We just take the area like this under the graph. Let's say we're going out to 5 seconds. Here's our area. And what's that? Well, that's a triangle. And the area of a triangle is half height times base, and that will give us the displacement for this case where we have a non-zero constant acceleration. So how far does this bicycle travel in 5 seconds? Well, we've marked out our triangle where our 5 seconds is here, and then at 5 seconds it really reaches this point up here, 6 meters per second. I know the red thing doesn't go all the way up there, but we'll fill it in. Okay, so the area of that triangle will be 1/2 the height, which is 6 meters per second, times the base, which is 5 seconds. You multiply those two together and divide by 2, right? Because there's the half of the area of the triangle. We get 30 over 2. We get 15 meters. So that would be the displacement this time. When you're given these problems, make sure you read this, right? Because sometimes when you see a graph and you want the area under it, you go right to the last point somewhere over there and find this whole thing. Well, that would be incorrect. Make sure you're at the right time. Next question, how can we find the displacement when the initial velocity over here is not 0? We've shown how the displacement is the area between the graph of v, the curve that shows the velocity, and the horizontal axis, time, during the given time interval. But what if the area is not a simple rectangle or triangle? Well, we have some steps here. First, break the region into rectangles and/or triangles. Then find the areas of the individual shapes, where the rectangle is height times base, and the triangle is half times height base. Then add them all up, and that will be your displacement. This graph shows the velocity versus time for a girl starting a run. How far does she travel in the first 10 seconds? First thing, make sure you mark off the time that we're interested in. In this case, it's 10 seconds, so it's using the full graph. But if they had said in the first 4 seconds, you would have terminated it right here. So let's break it into a rectangle and a triangle. Here's our initial velocity. This piece gives us our rectangle. Okay. Then what do we have? We have an acceleration or an increasing velocity, and that's our triangle. So we're done with the first step. Let's work with the triangle first. We have a base of 10 seconds and a height of 4 meters per second. Well, where did that come from? Well, we went from 2 to 6. 6 minus 2 is 4. So the area of the triangle is 1/2 times 4 meters per second times 10 seconds. And what do we get? We get 20 meters. Now let's do the rectangle. We have a height here of 2 minus 0, so that's just 2 meters per second. We have the 10 seconds again for our base, and that gives us 20 meters. Finally, step 3, add up the two areas. 20 plus 20, we get 40 meters. That's the displacement. To find the displacement, delta x, when the initial velocity was not v0 equals 0, right here you can read v0 is equal to 2 meters per second, we divided the area under the velocity time graph into a rectangle and a triangle. Can we now express that as an equation that will also work to find the displacement? Well, yes we can, or we would not have asked the question. So let's look at the triangle first. The area of a triangle is 1/2 height times width. So what's the width of the triangle here? Well, that would be t. And what is the height? Well, it's velocity at any time minus the initial velocity. So that's going to be v minus v0. So the area of the triangle is 1/2 v minus v0, all of that times t. The rectangle now has a width here of t for time, and its height is a constant v0. So the area of the rectangle, height times width, v0 times t. So the total area under the graphed line, is v0t plus 1/2 times parentheses v minus v0 times t. The total areas will now be equal to the displacement of the object or the runner. So we have delta x is v0t plus 1/2 v minus v0 times t. Now what is v minus v0? Well, we define acceleration as final minus initial velocity over time. So you do a tiny bit of rearrangement there, and v minus v0 is equal to at. Substitute at in for the v minus v0, and we have delta x equals v0t plus 1/2 at times t. Multiply through by t, and we have delta x is v0t plus 1/2 at squared. Since delta x is x minus 0, we'll go ahead and substitute that in for delta x. We get x minus x0 equals v0t plus 1/2 at squared. Put x0 on the other side, and look at this. We have kinematics equation number 2.